Okay, well, so last time, well, first of all, thanks for meeting on Zoom. I have a 12:15 doctor's appointment here in Grafton, so it was going to be a rush getting from campus to the appointment. Where right now I'm 7 minutes from the appointment, so I will make it in time. In any case, we talked about Huffman codes last time. We didn't look at any implementation of it. I'm kind of what I'm trying to do here in our last week is pull together some of the things, applications of things we've talked about this semester. We'll look at some other things today, dealing with effectively the base of a linked list, and we'll talk about hash tables a little bit. Now, having said that, all of you have heard of blockchain at some level. Anybody want to take a stab of what blockchain is? Here, I'm gonna, just so you don't read. What do you, based on your perception of what you see in the news, have heard, things like that, what do you think blockchain is? Or what are some things, what are some buzzwords that pop into your head when you hear somebody reference blockchain?
I know you did explain this to me once. I completely forgot, but all I know it has to do with NFTs and stuff and personal ownership, I believe.
Okay, so NFTs are a newer thing, and we'll talk about that. But you're right, NFTs are involved. Yep. Let's see. All right, Griffin says crypto buzzword. Yeah, absolutely. So let's take it a step further. When you hear crypto, what are some things you think about with crypto? You start thinking about things like Bitcoin and Ethereum, or maybe our two popular ones. You roll back 4, 5, 6 years, other ones that were in the conversation back then that are still traded today, but are less known today, are things like Litecoin. When somebody says cryptocurrency, what does that mean to you, that general idea? So it's true that cryptocurrencies are based on a blockchain, but when you hear cryptocurrency, what do you think? What is the idea of a cryptocurrency? What is it trying to accomplish?
It's trying to be a currency outside of government restriction.
Okay.
Just all digital.
Yep. So we think of it as the idea like, okay, the US dollar for us, we can say, well, that's not good enough. So we need an alternative currency, and the proponents of cryptocurrencies, let's just say for our intents and purposes right now, the proponents of cryptocurrencies would say that they're better because they're not controlled by a government. They're not controlled by any single person. Okay, fair enough. Now, truth be told, we're nowhere close to grandpa buying milk with Bitcoin. Now, an interesting thing here is that, you know, if we look at how we spend money these days, we might say that it's pretty common for us to have our money exist completely digitally, right? You know, we probably all carry around some physical money. You know, you need to throw something into a vending machine or tip someone somewhere or something like that. But in general, we're carrying debit cards or credit cards or other, you know, we pay people via PayPal or Venmo. So these are all, you know, digital ways of dealing with our currency that just moves money, moves numbers from one bucket to a different bucket. All right. But so the real difference here between, if we just think of it at the high level, between a cryptocurrency and let's say something like Venmo, there was Cash App or PayPal, doesn't matter. PayPal is a really good one because it's a company that's been around for a long time. All right, so let's say that you're paying me $10 using PayPal, and you expect that I'm going to send you, I don't know, a concert ticket or something like that. If you pay me $10 and I don't send the concert ticket, what do you do? Or what can you do? You can contact PayPal and complain, right? you probably contact me first and say, hey, what's the deal? You didn't send me the ticket. And then let's say I ignore you or whatever. And, you have recourse. You can go and contact PayPal, scream and yell and say, hey, yeah, I gave this person $10. They never sent me my item. What's up with that? And PayPal can decide what to do. They can handle the dispute, and ultimately, they act like the judge and the executioner, right? They get to decide if they're going to refund you your $10, but at least you have somebody to scream at. With a cryptocurrency, if we have, replaced PayPal in this case with, we'll just use the big boy as an example. It doesn't matter whether he's better or worse than other cryptocurrencies, but we'll say Bitcoin. If you give me $10 in Bitcoin, the equivalent of $10 in Bitcoin for these tickets, and I don't send you the tickets, you have no recourse. There's no individual person you can call, you can scream at, you can do whatever to ultimately try to get a refund for your Bitcoin. All right. Now, human beings, depending on what side of the coin you are, we probably don't like that, right? We kind of want our cake and eat it too. When you think about the big scheme of things when it comes to money, especially with the way the world works today. We're all about privacy. We're all about security until privacy and security make things inconvenient for us. And then we want somebody we can scream at. It's just kind of the nature of the beast. Now, having said that, these are all discussions about whether, what will blockchain be used for? What will, is cryptocurrency the killer app for blockchain? Or whatever. So these are really more emotional, political type of discussions. What I want to do is I want to move past that and think about what's the underlying data structure that anything based on blockchain utilizes. So this is Bitcoin, Ethereum. This is any of these things that we're calling cryptocurrencies, regardless of how much they actually are used or actually behave like currencies. These are also these newfangled things called NFTs, which we'll talk about. So there's all sorts of uses of blockchain. But the thing that kind of dominates the news is this phrase cryptocurrency, which is, like we just kind of talked about, it's kind of problematic for human beings. It becomes an interesting thing. We like to complain about the super rich, like Amazon, for example, but at the same time, Amazon is the most popular shopping destination in the world because it's convenient. And if something goes wrong with a purchase from Amazon, you can call up and scream at Amazon and they make it right. So most of us, whether we like Amazon or not, we would trust that if we sent $10 US in an envelope to Amazon, that they would send us our package. They've established that level of trust, even though we might complain that, oh, they're not paying taxes or all these other political issues that we might not like, but we still benefit on one side. And when we're benefiting, we're happy. When things seem unfair, we like to complain, but not at the cost of our convenience. All right. So for us in here, we want to think about blockchain as a data structure. All right. So I want our mindset to start off in an area similar to linked lists. All right. Because blockchains really are based on top of the idea of a linked list. So the blockchain data structure is a backed linked list of blocks. We'll talk about blocks a little bit here in a second. We're going to talk about it at a pretty high level, not super details. Of transactions, which is ordered. It can be stored as a flat file or in a simple database, but we would think about it as a linked list that lives in a computer's memory initially. And then the idea when we think about a blockchain, instead of it living in a single computer's memory, what we're going to do is we're going to replace the computer's memory with the memory of the internet. All right. So we're going to throw it out there on the internet. And now all of a sudden, lots and lots and lots of people's computers, let's say, hold duplicates of the blockchain that all must agree with each other. So now you're not reliant on a single point of failure, like your computer shutting down. You're not reliant on, a historical thing that kind of sort of acts like blockchain from a cryptocurrency perspective, like Visa or MasterCard, who are managing money going back and forth. You're not reliant on a bank, something like that. You're effectively reliant on a population of the internet that duplicates the storage of data over and over and over again, so that changing that data would be, let's say, nearly impossible. All right. So each block, we can think of a block as a collection of transactions. Transactions being like, hey, I bought milk, or I paid $10 for concert tickets, transactions between two parties. So each block is identifiable by a hash. All right, so first of all, what's a hash? I think we've mentioned this before. A hash is a one-way cipher. So arbitrary size data, in this case, a block with n transactions. And we don't necessarily know how many transactions happened in the most recent block. And different cryptocurrencies have a different algorithm, whether it's all the transactions that happened in the last 10 minutes or the last 3 minutes or the last 1 minute. Doesn't matter. They all basically work the same way with little variable changes. So we're talking about it at the generic level here. So there was n transactions in the last period of time, and those transactions get loaded into this block. So we don't necessarily know what the size of the block is. It's probably got the average size of a block is going to be in some sort of range. So arbitrary size data is run through a hash function. In our case here, it's going to be one called SHA-256. And a fixed sized output is produced. All right, so the idea is that you have literally an infinite number of different kinds of inputs, but you have a fixed size output, which could lead to something called collisions. All right, so just kind of remember that general idea here as we go through this. All right, so each block is identifiable by a hash generated using the SHA-256 cryptographic hash function on the header of the block. All right, now one specialty thing of SHA-256 in our case here, and the way it's used, and we won't go into the details of this, is it actually is collision free, which means you will not get the same output for two different inputs using SHA-256, and that's kind of provable through math. So just sort of trust that in our description there. Bottom line is every single block that's created is uniquely identifiable by a hash, and an important aspect of a hash, it is not reversible. We cannot get the original data from a hashed value. Okay, so if that block is run through SHA-256 encryption algorithm, hashing algorithm, and we get a fixed value, we have no way of taking that fixed value and somehow unhashing it into the original list of transactions. All right, so that's secure, but also we might say, okay, well then what's the utility of a hashed value? If I can't get the original data, how are we going to use that hashed value? What is it ultimately going to be used for? All right, so when we look at this, this is just kind of a high level of a hash table. You might have different inputs and they boil down to the same output. And here's an idea of a collision where maybe Alice and Dave both hash down to the number 152, which then has a couple different values stored there. It becomes kind of problematic. This is an example of collisions. Well, we don't have that in the with SHA-256 in the context of blockchain. So every single block will have a unique hash is the idea here. All right. So how does the blockchain actually work? I said in our mindset, we want to think about this as a linked list. All right. So we have a linked list of blocks that are linked together, these block data structures. So I'll read this first, then we'll look at this picture. So blockchain organizes data by splitting it into subsets referred to as blocks. Okay. Blocks are similar to the nodes of a linked list. Each block contains several elements. The elements of a block are generally separated into the block header and its transactions. While the transactions in a block account for most of the data, the block header contains essential metadata about each block, such as timestamp and kind of size of block. That's the block height. The main difference between a blockchain and a linked list, this is where it gets important for us, is that the reference in a blockchain are cryptographically secured. Reference being like a pointer to the next guy in the blockchain, is cryptographically secured. That's that SHA-256 thing, and therefore tamper evident. So if somebody tried to mess with it, somebody tried to insert some transactions that didn't actually occur, it would be obvious to anybody who would go and look at the blockchain. Okay. In contrast, the pointers in a linked list can be changed at any time without affecting the integrity of the data. So if you took half of a linked list and if you took a linked list and all of a sudden just took one of the links in a different list and set its next pointer to be the head of your new linked list, you broke the original one and you have this new list that just moves on with its life. No problem, no harm, no foul. Okay, it's because we have no way of validating whether or not the current state of the list, this new one that you just created, is actually wrong compared to the original. We have no way of knowing that that somebody broke our list without our knowledge, something like that. Okay, so the secured references establish order throughout the blocks and effectively make the blockchain an append-only data structure where new data can only be added with new blocks. All right, so effectively, and maybe this is a good thing if you remember back earlier in the semester, when we were writing our initial linked list, one of the harder functions to write in it was add and remove at index. So adding a node to our linked list at bucket 7, for example, or removing it from bucket 7. Those were more complex things to pull off. I usually referred to it as kind of like performing surgery, something like that. But they were difficult to pull off because we were having to do a lot of changing in connections and stuff like that. Well, a blockchain doesn't actually allow for that. And if somebody tried to do that, it would be obvious that they did it. You would be able to review the blockchain and say, oh, this blockchain, this pseudo linked list thing is not in its current correct format. All right. So we're looking at a augmented version of linked lists, a linked list with additional security laid on top of it. That's what a blockchain effectively is. Okay, so we're going to look at why this is the case. So we're claiming that a blockchain is something that we can only add stuff to the end. So you can add end to our blockchain. You can append to the very end of it. All right, so if we look at let me try zoom here. Oh, well, that was an interest. There we go. All right. And we'll kind of reveal what the issue is here, or what the security is here. So every block, so these nodes, we can think of this from our pictures. We had nodes. A block has two sections. We have this header section, and then we have our actual transactions. So these are the, send Bitcoin from this address to this address. Send Bitcoin from this address to this address. Those are our actual transactions. Okay. Not really important for us. These are the payloads of our nodes, if we want to think about it from our linked list perspective. Okay, now this block header stuff, this is actually important. All right, and we're only going to look at one of these things because there's Merkle root trees. Hash trees are actually another data structure that's being used here. Time, number of bits, nonce is like a unique value based on time usually. But we only need to understand this at the high level. We only need to look at the block header. All right. So notice the phrase used here, previous block header hash. Well, we already know what a hash is. So we know that a hash takes in an arbitrary size data and produces a fixed size output. And you can't reverse the original data. You can't get the original data out of it. So that means that if we just look at block one here, block one, as part of its data, as part of its header rather, okay, its header section, it holds the hash value that is the header of the previous block hashed. So my second node in our example here, we have a linked list of nodes, a linked list of blocks here. So block number one here knows about a hash that is only created by information from the node that came right before it, from the block that came right before it. And we'll see in the next slide that this would cause them then a problem if somebody tried to break this. Similarly, block two knows about block one, which knows about block zero. But when I say knows about it, it's provable. We can say, is the current guy that came before me, is that guy the real guy? Because we can go and we can calculate the hash on block one's header. We can run that through the SHA-256 hashing algorithm and get the same answer every single time. Okay, so we can take this header from block one and we can calculate it. That value should match this hash value that is in block two. And keep in mind, when we hashed the block one header, part of that hash, part of the data that we were hashing was the hash of the block zero header. When we hashed the block two header, part of the data we were hashing was the hash of the block one header plus the hash of the block zero header. So our data becomes more and more unique. The more transactions, the more blocks we end up adding to the blockchain. All right. So again, it's append only. We can't add stuff here in the middle because if we try to add something right here in the middle, we now break this association between block one and block two, where block two thinks his previous guy is block one, but now you've put a new dude in there that this hash doesn't match up. So what we should take from this slide is it's pretty secure. Changing data in the middle is going to be problematic. Okay, so the hash value of the previous block header is included in the following blocks as a reference because the block hash depends on the data of a block. Even changing a single character in one of the transactions would invalidate the reference. And that has to do with how hashing algorithms work. Even if you changed one bit in a collection of data, it is highly, 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 highly likely that it would produce an identical hash to what it did before. All right. So even changing one bit would produce a different output for a hashing function, which would then make, and if we look at this picture here, if we go from block zero, and here's our real block one, so what we have here on top is what our chain looked like from before. And now we have this malicious actor come in and they try to say, hey, we're gonna fake block one because we want block one to have some transactions in it that maybe give my wallet a whole bunch of Bitcoin that I didn't deserve, something like that. They're trying to steal money, steal something. Okay, so all of a sudden, this block one header, if we try to go in and change the blockchain, because initially block zero, block one, block two all existed. So our chain, and maybe this is just a portion of our chain, but this chain already existed. Maybe there's some other blocks later on, doesn't really matter in this example. But then some malicious player goes in and says, okay, I'm going to try to insert fake transactions in this particular block. Okay, because remember that our transactions here are public. Okay, these are not encrypted. the transactions themselves. Now, a transaction doesn't look like, when we think about like a Bitcoin transaction, it's not going to be Mike sends 3 Bitcoin to Dave. That's not how it's going to look. It's going to look like this crazy looking wallet address, some big hash value, sends this number of Bitcoin to some other crazy address looking thing. Something that would be, for our intents and purposes, by looking at the blockchain, let's say, impossible to trace back to an actual human being using this data. Maybe we can go and, get some sort of investigator or something like that. And, if we kind of look at how a person is spending their Bitcoin, we might be able to determine that, oh, this, this person sends transactions on every Monday, Wednesday, Friday at a certain time. And maybe we can kind of figure out what IP address they're coming from or something like that by doing network sniffing, whatever. I don't want to advertise that it's impossible to find out who a wallet address belongs to, but it's not held inside the blockchain itself. That would be a whole nother investigation. Okay. So the idea here is that these transactions are plain text. They're not encrypted. And these are all the things that happened in the last block. All right. But so the idea here is this malicious player would say, oh, I'm going to change up and say that some address sent me 4,000 Bitcoin. Just because I want to fake the transactions so that I have more money now. All right. But what ends up happening is block 2's previous block header hash is going to match block 1's header, not this new fake block 1's header. So this guy we would be able to invalidate him and say, hey, when I calculate this block's headers hash and this block's headers hash, only this guy matches the next block's previous block header, not this guy. So this guy's off limits. We're going to disregard him as part of the blockchain. All right. So changing a blockchain in the middle is something that we can't do because of the way blocks are stored. Now you have to couple this and say, well, if we're just looking at this strictly from a data structure perspective, and we pretend like this blockchain exists only on a single computer, it's still pretty secure, right? If we think about like we're trying to represent a database here on a single computer, and a blockchain is not necessarily a good way of representing a database. It's very memory inefficient from that perspective. We're not trying to be memory efficient. We're trying to be secure. All right, so it's got a different goal. But let's say we were on a single computer here. We would still be able to see that if somebody came in and tried to make a change on this single computer's data structure, this linked list of blocks, we would be able to go back through and say, let's check the validity of our linked list and see that, oh, something is wrong with this guy. Okay. He's broken. Why? Because this guy right here, this previous block header hash, validates this as being the accurate block on the chain, not this guy being the accurate block on the chain. So the fact that each block knows information that is calculable from the previous block adds to the security. Okay, so it's a linked list with additional error checking, or a linked list where one node is mathematically connected to the next node. All right, so each new block built on top of an existing block is called a confirmation. All right, so we're effectively confirming the previous block by having the next block hold its hash. And like I mentioned a minute ago, this isn't represented on a single computer. This is represented thousands of times across the internet. So we don't just have, by this picture here, we don't just have a single copy of block 2. We have thousands and thousands of copies of block 2 that all have a hash value inside them that should be calculable, that should be validatable if that's a word, let's pretend that's a word, against the thousands and thousands of copies of block 1 that are on the internet. All right. So those thousands and thousands of copies of block 1, we can calculate the hash of the header here and compare it against the value stored in block 2's header that's stored thousands and thousands and thousands of times. And we can confirm that, you know what, a high majority of these guys, probably all of them except one in this example with a malicious player, but even if it's 90% of them, 90% of the block 2s that are out there support this guy being the true block 1, where a much smaller percentage support this guy as being the true block 1. But keep in mind what actually has to happen in order to actually modify the blockchain. This is a simplified example, right? Because what actually has to happen in order to insert this fake block 1 here, you not only now need to modify block 2, you have to modify block 3, which modifies block 4, which modifies block 5, because all those guys are built in terms of the hash value of the dude who came right before them. And even making a tiny change to this header will produce a different hash value. So it becomes mathematically impossible to modify the blockchain. Your best bet would be to modify it at the most recent block, because then you have to do the least amount of updates. For us to go back and modify a block from 4 years ago, for example, would mean that we would have to then have some sort of way of updating the header of every single block that's occurred since then. That becomes not a thing. Okay, we really can't do that. So the security of blockchain is built into that at the cost of memory efficiency. So if we go back to how we originally thought about linked lists, when we were comparing them to arrays, we said linked lists are relatively slow, but they're memory efficient. All right, because when we were thinking about this in terms of a single computer, if we deal with arrays, we needed a bunch of contiguous memory right next to each other. Whereas if we're dealing with, so that means that if we were going to store a bunch of data, we needed a whole bunch of memory right next to each other. But that also makes it fast because we can mathematically calculate what bucket of memory a certain element of our array lives in. A linked list says we no longer need to know about how much stuff we're going to store initially. We can now just build as we go, and as long as we have enough available memory for the next, in our example here, the next block or the next node in our linked list, as long as we had enough memory, we could then just instantiate that and have a pointer link to it. No harm, no foul. Now, that is fine when we deal with a single computer from a memory efficiency perspective. Now, when we jump to the idea of blockchain, we're effectively saying we're not going to just store our linked list on one computer. We're going to store it on thousands of computers, and they all have to agree with each other. We're adding a layer of security to our linked list, and that layer of security is being accomplished by producing these blocks multiple times, as well as applying a hash algorithm. Nothing necessarily says that I have to store these as a linked list. I can certainly store these guys as an array, right? Because the only thing that we don't necessarily care that this guy is in a different memory location than this guy, or that they're not next to each other in memory. All we care about is who is block 2's real neighbor. Is it this guy or is it this guy? Who is his legal neighbor? We don't care where he lives. We don't care how this is represented. But now when you think about the fact that we want to have this duplicated thousands of times on the internet, we're now moving beyond our physical computer, where we have to work out of the limitation of how does memory work. All right. And now we're saying we're going to be storing this blockchain on the internet, whatever that means. It's going to be stored in in a cloud somewhere. It might be stored on an individual person's computer. So now instead of it being stored on a single computer's memory, it's going to be stored on, let's just keep using my example of 1,000 different computers' memory. And those 1,000 different computers have their own limitation of memory, whatever that is, and they all have to agree on what the current state of the blockchain is. So blockchain does not try to be, does not try to have a small footprint. It's memory inefficient from the perspective that we are storing the data a whole bunch of times. It's memory efficient relative to using an array to store this, because when it is stored on a computer, all the blocks don't need to be right next to each other. The current size of the blockchain, let's just go and look that up real quick. Current size of Bitcoin blockchain. It's going to give us and what is, so it's 378, is that, I think that's gigabytes. Yeah, gigabytes. So that linked list currently is 379 gigabytes for the Bitcoin blockchain. Now, keep in mind, this guy has been around for a long time. The original, well, let me get to it from here. You know, first block for Bitcoin. January 3rd, 2009. All right, so this was the Genesis block. So every 10 minutes, roughly 10 minutes, because that's the algorithm that Bitcoin uses, that every 10 minutes a new block is born. So every 10 minutes-ish since January 3rd, 2009, a new block has been added to that linked list. So now we're at the total size at 379 gigabytes of data. Okay. None of us have 379 gigabytes of RAM in our computer. So now we start seeing the memory inefficiency of even storing that linked list once. But now, so we have to store it in parts across the internet or something. But now I'm saying we're actually storing it thousands of times, thousands and thousands and thousands of times. So it's not just 379, it's 379 times thousands and thousands of times. Tons and tons and tons of data just to support the security of the Bitcoin blockchain. And we're doing this, when we think about this from the perspective of cryptocurrency, we're doing this to fix the horrific problem that we have today. That is, we are not able to walk into Sendix and buy a gallon of milk with $3 US, which we are able to do, right? We could buy our cheeseburger, we can buy our milk. The US dollar is working just fine. The things that we push back against it for is inflation and stuff like that. The government can just decide to print more money just arbitrarily, and that causes its own issues. Where Bitcoin, every 10 minutes, new Bitcoin is born. Okay, a little tiny fraction of Bitcoin is, well, actually more than a fraction, but the reward comes out to the people who are actually mining the Bitcoin as a fraction, because they only contributed a little bit to the validation of that chain. I'm not going to get into that side of things, but basically every 10 minutes, when this block is added to the end of the chain, before it's allowed to be added, it has to be validated, and that's done by what you've heard of in the news and stuff, by these people called Bitcoin miners. All right, so these are people with computers that are solving this math problem, proving that this guy is the legitimate next block that will be legitimately added onto the official blockchain, so that from this point forward, that is the current state of the blockchain. And that's a whole other security thing of it. We want to focus on the data structure side of this. So we can just say this is what the blockchain looked like. Somebody's going to try to manipulate the data. That's not going to be allowed. Okay. Let's see. We kind of already talked about this. Well, okay, so I like this word, the immutable word. It is important to note that it is not the data structure that makes data on the blockchain immutable. Immutable means not changeable, as opposed to mutable means changeable. It's kind of an older programming term or something like that. I'm sure it predated programming, but mutable is changeable, immutable is not changeable. The information alone is tamper evident only, so we can see when somebody tried to mess with the blockchain. Okay, under scrutiny, we can see that, oh, this link is not a correct link. So changes are easy to detect. There is no immutability if there are no strong consensus rules in place. What I mean by consensus rules, we mentioned this earlier, is, like I said, nothing keeps an individual person from presenting an updated blockchain and saying, oh, this is actually the true blockchain, with their, little malicious attempt here at replacing one of the blocks. Nothing keeps somebody from doing that. It's the consensus algorithm that's in place where all the people that are mining Bitcoin, all the people that are involved in that blockchain, look at their current state of the blockchain and compare it to everybody else's current state of the blockchain and come to a consensus of what is the correct state of the blockchain, preventing somebody from adding a malicious block like this. All right, so we're going to say that that's secure. You would have to circumvent those consensus rules in order to pull that off. And if you wanted to go and read about that, there's a famous thing called the 51% problem, where if one entity, a single person, or one can just think of it as a single pool, a single person, if one person controlled more than 51% of the computing power that is in charge of validating the current blockchain, they would then have the ability to rewrite the blockchain and outvote the other players in the consensus. All right, so if somebody owns 51% of a company and you have a vote of the board of directors, it doesn't matter how everybody else votes. The way it's going to get decided is by the person with 51% of the company. Their vote means more than everybody else's combined. So one of the things that we prevent with the validation process in Bitcoin mining is this idea of allowing any single entity to have more than 50% of the computing power in the process of validating it. Realistically, it typically gets suppressed to at most like 20% or something like that. And that really is self-policing, because all of the different entities that are involved, these are individuals, you or me could go and mine Bitcoin, or there's these large companies that are, professional Bitcoin miners or whatever, that have really powerful equipment. You or I, if we were going to mine Bitcoin, we would probably go and mine with one of the Bitcoin pools out there, where it would be, me and my 4,000 friends that all decide to, mine Bitcoins under the same flag. And, when we are the validating winner, we split the profit of the new Bitcoin that were born for that particular block. So that's how it's validated at the high level. All right, but as long as one entity doesn't control more than 51% of the computing power on the validation network, the blockchain is secure. because this idea of the consensus rules will stay in place and things like this won't be able to happen. All right. And a sufficiently large number of nodes on the network. So as the blockchain gets larger and larger and larger, so we think of Bitcoin here with 379 gigabytes of data in their blockchain. In order to change one block would require us to change so many other blocks that it becomes mathematically impossible to do that, even if we remove the idea of consensus. So the longer a blockchain is, the more mature a blockchain is, the more secure it becomes, especially in its older transactions. The older a transaction is, the more secure that transaction becomes because the more validated it is. If you're transaction 100 and you look at if you're block 100 and you look at block 500, there have been 400 blocks in between there that are all at some level based on your hash value. That's a lot of stuff that has to change in order for you to get modified maliciously. All right, so just in our last few minutes here, and we'll pick up next time. We'll also talk about the final exam next time, but current shortcomings. The development of blockchain is stricter and slower compared to traditional databases. So I mentioned this earlier. If we're thinking about this guy as a database, which isn't a good use of blockchain, it's going to be slow. This is not what Amazon is going to use to look up what your order status is for your collection of orders. It's not going to be fast. It's just going to be secure. And now we have to say, well, is a traditional database under the right IT management secure enough for the job it's solving? We might say if we're dealing with currencies, we expect it to be more secure. But what I'm going to argue next class is that currencies actually are not the killer app for blockchain. I would actually argue it's the problem with blockchain. This new thing that's becoming popular now are these things called NFTs, which are now finally using blockchain for kind of an appropriate use, which is ownership. So the security of ownership is really, really, really important. You know, if you own your house, you don't want there to be somebody else who comes along and says, oh, I actually own that house. And now there's real debate on who owns the house. That's something that's very important to protect, and that's ownership of items. And that's where this idea of NFTs come in. The currency side of blockchain can be valuable for short-term transactions. There's a currency called Ripple and another one called Stellar Lumens, that both solve a similar problem. They look at the banking problem and say, okay, well, the United States banking system is incompatible with, let's say, the Chinese banking system. These are two completely separate networks. And if you want to get money from one of those banking systems to the other banking system, there needs to be some sort of transport protocol. So there exists a couple of blockchains, Ripple, which is XRP, and Lumens, XLM, that exist solely for that transport. So you would turn 100,000 US dollars into Ripple. It would go across the Ripple network. You would then turn that 100,000 US dollars worth of Ripple into the equivalent amount in the Chinese yuan. All right. So at that point in time, you've temporarily represented currency on a blockchain, but only for transport between two incompatible banking systems. That's a legitimate use of Bitcoin or legitimate use of blockchain that is in the realm of cryptocurrency, but it's not, you're not buying milk with Ripple. You're just representing value for a short period of time to link to incompatible networks. These are reasonable uses of it. So that's what we'll talk more about next time. But database is not one of those things. Okay, so we'll cut it off right there. Are there any questions, comments, concerns, bribes about what we talked about today? I want our focus to really be on, this is a specialized and enhanced version of a linked list, things that we've spent this entire semester kind of looking at. not is Bitcoin good or something like that. That's a whole nother argument. Okay, well, I will see everybody on Friday and we'll talk about the final exam. If you are planning for next week, though, I will say that my plan is I'll put the final exam up as an online test. It'll be up by Monday morning. You can take it whenever you want during the week, but I'll make sure that I'm available live during the official final exam time if you want to take it during that final exam time and be able to ask questions or something like that. So you can decide how you want to time manage. Okay, I'll see everybody on Friday.